Hello everyone, welcome to our discussion of section 4.2 where we will be talking about the very important natural exponential function. So before I begin this section, please remember to skim through or read through this section 4.2, spend maybe half an hour or at most 45 minutes on this section before you watch the video. Then, as you watch the video, take careful notes about the questions you might have or about the important things that you might encounter in this video. And then review your lecture notes again or review this video and while you solve all the problems that you see in this section on your own without looking at my solutions. In other words, please pause the video and solve those problems again on your own without looking at these solutions. The same way with the examples you see in the book. And of course, please complete the homework assignment for this section by the due date and review any previous sections up to this point to keep everything fresh in your mind. Okay, so beginning with this 4.2 section, the natural exponential function is known as this function, f of x equals e to the x. So I often get this question, what is e? Well, the quantity e, you can numerically look at it in this using this formula that e is equal to 1 plus 1 over n to n power, where n approaches infinity. That symbol, those of you who will be taking Calculus 1 or Math 181, you will become very familiar with that symbol, that arrow. N arrow infinity means as n approaches infinity. So you will see that a lot in calculus classes in general. And so E is equal to that. And that means that if you pick n to be something small, let's say 100 or 10, you will not be exactly at E. So E is achieved when n becomes extremely large, as if it gets close to infinity, 100 billion, tens of millions, if not hundreds of billions. So when n becomes that large, then you will reach the value of E with this calculation. So what is the value of E? E is an irrational number. That means its digits never end. The decimal values continue forever. But the first few digits of E can be summarized as this, 2.718281828, and so on. So, and this number has so many applications in mathematics that it has its own button on a scientific calculator. I presume because it has applications in business as well, so I assume even in business calculators it has its own button. But on this calculator, I don't know if you can see, you probably can see it, but there is a button. See, ln, we will get to that. ln is natural log. It stands for natural log, ln. Right above it, in blue, there is the e to the x button. I don't know how clearly you can see that on the screen. Maybe if I move it here. I think that's a little bit better on the screen. So let me activate that button with x equals 1. In other words, we're going to calculate e to power 1. I want to do that so you can see that number on the screen and compare it with the one that I have on paper here, right here. Okay, so I'm going to activate the blue button e to the x by pressing that second, and then e to the x. See, the x part or the variable part is left blank, so it's ready for me to enter a number. I'm going to enter 1, and close the parenthesis, and then hit enter. Now compare that with this number, right? They're identical. But as I said, this is an E is an irrational number. So it'll never end. So these are just a few digits that the calculator can show on the screen. Okay, but it'll continue forever. It has many applications in the natural, scientific, and the business world. One of the things we didn't, for example, look at in the previous section, well, we looked at compound interest, right? The other formula that we didn't look at was the continuous compounding formula. I'm sure those of you who are in business, you will see that formula in your classes. And it is called continuous compounding of interest formula, okay, which makes use of this quantity E. All right, so the way the graph of the natural exponential function looks is shown in this graph. So the one, when I printed this, it came out black and white, but the actual graph was in color. So y equals 3 to the x, which is an exponential function, has that graph. Y equals 2 to the x has that graph. And y equals e to the x, which is the natural exponential function, right? This is the natural exponential function. Is right in between those two graphs. So that's the graph you see in the middle. Right? And it makes sense because the base here is 3, the base here is 2, and the base E here is 2.71828 and so on. So that E is between 2 and 3. So it falls right in the middle. Okay? So it is a natural exponential function, which is that quantity. And we said that you can calculate this number closer and closer to it, to its actual value, by calculating this formula as n approaches infinity. So you take, if you want to do this manually, you can, as just if you're curious, you can take n to be 100, then n to be 1,000, then 10,000, 100,000, a million, 10 million, 100 million, 1 billion, and so on, and see how this quantity approaches that E value that we talked about, 2.71828, and so on. Okay, so I'm sure you noticed that the graph of the natural exponential function is an increasing. It's a rapidly increasing graph. So that itself is a rapidly increasing exponential function. Okay, that's also important to note. So y equals 3 to the x and y equals 2 to the x, these are exponential functions. The natural exponential function is what you see me as having boxed here. E to the x is called the natural exponential function. So here it says, number 1, exercise for us. It says, take a look at the graph of the natural exponential function above, which we have here. It says, take a look at that. Right? We have it shown in red here. And use the interval notation to give the domain and range of the function. Very well. Okay, so the domain, as we've discussed before, is the behavior of any graph with respect to the horizontal x-axis. Right? So if you look at the behavior of this graph, if you can continue this line on both sides like that. Is there any restriction along the x-axis? Absolutely not, right? This graph, as it's shown, and that function, natural exponential function, is able to take any value along the x-axis with no restriction whatsoever. So if that's the case, then the domain of e to the x, and this is y, is equal to, let me move this up a little bit, is equal to negative infinity to infinity, right? There is no restriction. How about the range? The range, as we talked about before, is the behavior of any graph of any function with respect to the y-axis. Okay, so what does this graph do with respect to the y-axis? If we continue it, you'll see that this line, this graph, has asymptotic this x-axis has asymptotic behavior toward the graph of the y equals e to the x. The reason is that even though this quantity can get very, very close to 0 for negative values of x, right? If x values are negative, which and it's obvious from this graph, if the x values are negative, this quantity, natural exponential function, becomes increasingly closer and closer to 0. Okay, so we do have a limit on the lower side of the range, so it cannot go below the y value equals to 0. This quantity can never become negative as a whole. Okay, unless of course you put a negative here in front. Yes, if you put a negative in front, you will change it won't be the same function anymore. You're going to flip it across the x-axis, as we learned before, right? If you put a minus here. But as it is, as you see the natural exponential function like this, there's no way this quantity can achieve 0. Okay, so or become negative. That's what I wanted to emphasize. It won't be negative unless you put a negative in front. So because 0 is what this graph approaches, or this function approaches, without actually being able to attain that value, we say parentheses 0, not bracket, right? Bracket means 0 is an attainable quantity for this function, but 0 is not attainable for this function. So parenthesis 0, comma, on the high side, this function has no bound. It'll go higher and higher. It'll increase without bound. X, the larger the x, the higher the value of this function. So on that side, it approaches infinity. And again, parentheses. So that's the range of the natural exponential function. Okay. So we have that. Then with this exercise, I wanted to make sure, because I've seen this every time I've taught this, people have trouble entering or calculating values involving the natural exponential function. So I wanted us to have an exercise here in class to make sure that everybody can calculate this natural exponential function like that with different values of x, just making sure. Okay, so for example, that for the first value of x, this is the function we're evaluating at different x values, right? Okay, so that will be equal to e to minus 2 times 1.5, right? Because x is 1.5. So that means e to minus 3 power. Okay, so let's calculate that. All right. Let me see if I can put this where you can see everything very clearly, like that. Okay, that should be a good position for the calculator. Okay, so we activate the E button on the calculator. If you don't do this, you'll have to say 2.7182818 to some power, to this negative 3 power. But I don't want to do that. I want to use the calculator button. And then inside the parentheses, I enter -3 and then hit enter. So that's the quantity. And this being an exponential function, I'm going to keep at least 4 digits. That means 0.0 or 4 decimal places. 0.0497, I could stop there. But I want to keep the 8 and round it to 9. So I'll write down 0.04979. Okay, let me write that down. 0.049. 4979, like that. Okay. How about this one? H at the function h at x equals -4. Well, that would be e to -2 times -4 equals e to +8. So let's calculate this quantity. E to the 8, I activate the E button again, E to 8 quantity, enter, and we have that, right? 2,980.96. I'm going to round that 0.95 to 96. So 2,980.96. Okay, like that. So I hope this is you're able to get the same results from your calculator. That's what this exercise is all about. So please, whatever calculator you have, take it out of your backpack and use it, and make sure that you can work with these buttons and get these values. Okay, and the last one is 1/2 or 1/2. So this will be e to -2 times 1/2, or -2 times 1/2 -1, or this is 1/e, right? This is the same thing as 1/e with a positive power. But let's calculate e to -1 power. See what we get in decimal terms. Okay? So I'm going to activate the E button again. This time I'm going to enter -1 as power. That caret that you see, that shape, that arrow, sharp shape that you see it's called the caret, and it means power on the scientific calculator. It just occurred to me that some of you may not know what that function does, or what that symbol means. That symbol means e to power -1. Okay, so here we have the result, 0.3678 and then 7. So I'm going to round this to 0.3679. Okay, 0.3679. So I'm going to keep 4 decimal places like that. Okay, so here they want us to graph this natural exponential function, which is of course manipulated somewhat, right? We have a minus in front, then we have a -x there in front of a minus or negative symbol in front of the x. By plotting a few points, hint, use x values -3, -2, -1, 0, 1, 2, 3. So let's do that. So I'm going to, where would I do that? Let me do that here. It's going to be tight, but I think it's better if I do that here. So we're evaluating this function, and x values X values are as, let's take them as these, -3, -2, -1, 0, 1, 2, 3. Okay, so let's calculate the X values. Or Y values, sorry. So minus e to minus x power, right? Minus x, that would be minus 3. So that minus in the power will make this minus positive. We will have positive 3, like that. So minus e to positive 3 power. So that is minus 20. Let me round that to minus 20.1. For us, that's enough precision. So minus 20.1. Okay, how about minus 2? Once again, before I actually calculate this, notice that when we replace x with minus 2, that minus in front of the x will make this positive. So this will be minus e to positive 2 power. Okay, so let's do that. So we have minus e to positive 2 power. That's minus 7.389. So let me round this to minus 7.4. Put minus 1 in minus x, so we'll have, so minus e to positive 1, right? Because minus x is minus 1 or positive 1. So minus e to positive 1 power, because this minus 1 will make this a positive 1. Okay, so minus 2.71828. Or let me round this to minus 2.7. Like that. And then 0, anything to 0 is 1, right? So if I put 0 here, e to 0 power is 1, but look at this negative in front. Minus 1 will make that a minus 1, right? So that would be minus 1. Then we reach these positive values, 1, 2, and 3. So 1 substituted for x, it'll be e to minus 1x power, right? So let's calculate that. So we have minus e to minus x, in this case is 1, so minus 1 power. So we have minus 0.3678. I'm going to round this to minus 0.4, right? Because for me, manually graphing this, I can only be so precise, right? I won't be able to do this like a computer would do. So I'm going to round this to minus 0.4. Then 2, substitute the 2 for x, we get minus e to minus 2 power, right? Because 2 being positive, when replaced in x, the power will be minus 2. Okay, so let's calculate that. So we have minus e to minus 2 power, and we have minus 0.135. So I'm going to round this to minus 0.1. Okay. And finally, with 3, when 3 plugged in here, we will have minus e to minus 3 power. right? But I mean, minus doesn't get, this minus in front doesn't get raised to any of those powers. That's why for power equal to positive 2, we still got negative numbers, right? So this minus is not going to get raised to any power, this minus in front. Okay? So, minus e to minus 3 power. And we have minus 0.04. So I'm going to round this to minus 0.05. Okay, minus 0.05. Okay, so let's plot these quantities. These are not, these are small numbers, and except that one. So let's see how I can increment my, if I make increments at, so these are y values, by the way. These are y values. And so for y values equals minus 20, that would be way down here. Let me move this up so you can see everything. So minus 20 would be way out here. So let me see. 5, 10, 15, 20. Yes, if I increment every 5, so this will be minus 5, minus 10, minus 15, and minus 20. That's along the y-axis. That's the farthest point we have. And along the x-axis, we have positive 3 and minus 3. Right? So let me do that. So 1, 2, 3, negative 1, negative 2, negative 3. Right? Okay, so let's plot these points. Negative 3 x value, negative 20.1, that would be roughly here. Somewhere here, right? Negative 2 comma negative 7.4, that would be negative 2 is here for x. Negative 7.4 will be somewhere here. So right there. Negative 1 comma negative 2.7. Negative 1, negative 2.7. Right there. Right? A little bit, because this would be negative 2.5. Negative 2.7 is a little bit towards, closer towards negative 5. Like that. Then 0 comma negative 1. 0 comma negative 1. If this is negative 5, so 0 comma negative 1 would be somewhere here. You can already see a pattern, right, emerging. 1 comma negative 4. So negative 0.4. Negative 0.4 is the y value. So 1 comma negative 0.4 is somewhere here, very close to the x-axis. 2 comma negative 0.1 is even closer to the x-axis. So clearly the x-axis is emerging as an asymptote for this function, right? And look at that. 3 is very, very close, because that's almost very close to 0 on the negative side of the y-axis, right? So it'll be very, very close to the x-axis. So now we have enough points to draw a graph of this function. Like that. Like that. Okay, so you do have this asymptotic behavior along the x-axis. Like that. All right? But we could predict this, right? Using the transformation of functions, we could predict this because so this function in red is the graph of minus e to minus e to the x. That's the graph of that. E to the x, as we saw on the first page, has this kind of behavior, right? So that behavior, let me draw it like with a dashed line. Something like that. So that would be y equals e to the x. So this, working this as the original function, this minus in the power would turn, right now this is an increasing function from left to right, right? That minus in the power would make this a decreasing function. So it would flip it. It would flip it so that it would be a decreasing function going like this. That's what it would happen with the minus x, with the minus in front of the x. And then this minus in front of the e would flip it across the x-axis as you see this final function shows itself like that after we plotted the points. Okay, so this minus in front of the x would make this a decreasing function first, and then this minus in front would flip it so it would become an increasing function. Okay, if you notice these connections, that's very, very important. Okay, so this was a short section. We have come to the conclusion of this section, and thank you for watching this video, and I look forward to see you all next time. So until then, have a nice day.